Hello, MAT 30 class, Calculus 2. This is my very first office video. I've never done this before, so this is going to be another one of those experiments. If this works well, I might do it a little bit more in the future, but I got to get the lighting down, I've got to get the volume and this all stuff down. So anyway, bear with me. The purpose of this video is going to be to do a very quick review of the divergence tests that you guys should know leading into this week. All right, so the first one is the geometric series. So a geometric series is of the form summation from n equals 1 to infinity of a sub 1 times r to the n minus 1, where a sub 1, of course, is the first term in the series and r is the common ratio. Well, we know that this series will converge when the absolute value of r is less than 1. It will diverge if the absolute value of r is greater than 1. So as an example, if we have the summation from n equals 1 to infinity of 3 times 2/3 to the n minus 1, we know because r is equal to 2/3, which is less than 1, that is going to converge. And we can figure out what it's going to converge to. The formula for convergence is a sub 1 over 1 minus r. So geometric series are easy. If you recognize that something is a geometric series, make it into a geometric series, and you can determine if it converges or not, and then you can determine what it converges to, a sub 1 over 1 minus r. The second series that you should know, just by inspection or by looking at it, is a p-series. So a p-series is of the form the summation from n equals 1 to infinity of 1 over n to the p, standing for power, right? And if p is greater than 1, it will converge. If p is less than or equal to 1, it will diverge. So as an example, if we have the summation from n equals 1 to infinity of 1 over n to the 5th power, then because p is 5, we automatically know that this is going to converge. All right, and that's all there is to it. If you recognize it as a p-series, maybe it doesn't actually look like a p-series, but if you can put it into the form of a p-series with a little bit of algebraic manipulation, then it's going to save you a lot of time. So those are two basic series that you should, by inspection or just by looking at them, be able to tell what they are and know how to determine if it converges or diverges. Because when you get into this week's work, the direct comparison test and the limit comparison test, you're going to use these types of series to compare other more complicated series too. All right, that brings us to the divergence test. The divergence test is a very simple test, and the divergence test basically says if the limit as n approaches infinity of the sequence does not equal 0, then it diverges. So if we have a series from n equal 1 to infinity of a sub n, we're only looking at the sequence. Remember the difference between the series and the sequence. A sub n represents the sequence. When we do the summation from n equals 1 to infinity, we are adding up all of the terms of the sequence, so we then have a series. So what the divergence test says is we just take a look at the sequence. We take the limit of the sequence, which we did a lot of that back in section 5.1 on sequences. You had to determine if a sequence converged or diverged, and that's all you're really doing. It's just taking the limit of the sequence. If it does not equal 0, it diverges. If it does equal 0, or if it equals any other number, L, we don't know. We can't say that it converges. All we know is that if it does not equal 0, it diverges. If it does equal 0, if it equals some, then we can't tell. Okay, so that's all we're looking for. So as an example, if we have the summation from n equals 1 to infinity, and I'm just going to do something fairly simple. Let's say n squared over 5n squared plus 2. And we want to determine if that is going to converge or diverge. The first thing that we generally do, you realize this is not a p-series. This is not a geometric. So I'm actually going to have to do some work. Then I like to start with the divergence test. Okay, tell me if I know if it diverges, I'm done. Okay, if it doesn't diverge, then I'm going to have some more work to do. So I take a look at this. I want to see if it diverges or not. And so one of the techniques that we have been using is to look for the highest power of n and divide everything through by the highest power of n. So I want to take the limit as n approaches infinity of n squared over n squared, 5n squared over n squared, plus 2 over n squared. We're basically taking and multiplying the numerator and the denominator by 1 over n squared. It's just an algebraic trick that we learned back in 5.1 that we can simplify this. All right, so this limit then becomes the limit as n approaches infinity of 1 over 5 plus 2 over n squared. Well, now when we take the limit of this, 2 over n squared, as n squared becomes infinitely large, this becomes 0. So the limit then is 1 over 5. So what does this tell me? It says the limit of the sequence is not equal to 0. It is equal to 1/5. So because the limit of the sequence is not equal to 0, this series will diverge. And I'm done. I know it diverges. I'm done. I don't have to do anything else. All right. And the last test that you should know going into this week's work is the integral test. And so the integral test will require you to do some integration. Hopefully the integration isn't going to be extreme. Most of the cases it's not. The example I'm going to do today is going to be a fairly straightforward integration. But the integral test basically says if you've got a series, summation from n equals 1 to infinity of a sub n, and you can create an integral that is approximately equal to it from n equals 1 to infinity of f of x dx. If you can create that integral, where this integral basically represents that series, so in other words, the function is basically a function version of the sequence, then both of them converge or both of them diverge, right? So if the integral, if we integrate this and it converges to some number, or if the value of the integral is some number, then it converges. And that means this also converges. If the value of the integral diverges, then the series diverges as well. And so that's the gist behind this. So if we have, as an example, series from n equals 1 to infinity of, well, I'm going to do something simple. It's going to be actually a p-series. I look at that, oh, it's a p-series, that converges, I'm done. But let's just do the integral test on it. I'm cheating, I'm doing a really easy integration problem. All right, so what I want to do is I want to create the integral from 1 to infinity of 3 over x to the 5th. Well, that's an improper integral, so we have to take the limit. So we're going to do the limit as n approaches b of the integral from 1 to b of 3 over x to the 5th dx. And I didn't put my dx in there. All right, so integrating this, gotta make sure I don't run out of boardroom here. Actually, I can squeeze a little bit more in down here. We're going to have the limit as n approaches b from 1 to, actually, let me just not put that in there. So this is going to be 3x to the negative 5th, which would be 3x to the negative 4 over negative 4. So we have 3x to the negative 4 over negative 4 evaluated from 1 to b. And let me just move that down a little bit. There we go. And so that's going to become a negative 3/4, negative 3 over 4x to the 4th evaluated from b to 1. And then as we evaluate this for b, we can see that as b approaches infinity, that term is going to become 0. And so let me erase the top part here. And so we have negative 3 over 4 b to the 4th minus negative 3 over 4 times 1 to the 4th. And so this is going to become 0 plus 3 over 4, which is 3/4. So that means the limit is 3/4, right? If the limit is 3/4, got to be able to see me. If the limit is 3/4, that means the integral converges to 3/4, which means the series converges to 3/4. Boom, we're done. All right. So we have just shown by the integral test that the series converges. We already knew that it converged because remember it was a p series. A sub n was 3 over n to the 5th. Well, if p is greater than 1, it converges. So we already knew that. So we're just kind of confirming by the integral test that the p series does converge. All right, so that's what you should know as you are going into this week's work. So I'm hoping you're going to watch this video before you get too far into the direct comparison test, the limits comparison test, and then the fun ones, the alternating series test and the testing for absolute convergence. And if you guys like this little video and it's helpful, I'll make another little video on each of those other tests. I'll do one for the alternating series. I'll do one for the direct comparison test. The direct comparison test can be confusing. So tell me if you like these videos in class. I'll see you in class. Hopefully this was helpful. Bye-bye.